So go ahead and look at activity 2 in your homework packet. Know that we are going to complete this in class together. It is going to require a laptop with Google Earth installed, Google Earth Pro. So be sure to come to class with your laptop ready. And if you don't already have Google Earth Pro, go ahead and download that onto your computer. If you don't have a computer, let me know. I will bring one in for you tomorrow. Okay, so originally people did not believe Marie Tharp, and it took decades for more and more evidence to come out that supported her hypothesis of plate tectonics for people to finally say, okay, yes, you are correct. So it was questions well into the 1950s. So 20 years after this first discovery. And that's because more evidence needed to be discovered, published, extensively reviewed. And as frustrating as it is that she didn't get immediate recognition, this is how science works, right? Just because one person found one thing does not mean the entire scientific community is now going to believe this new revolution or revelation, right? It has to be extensively reviewed, agreed upon in order for the community to finally call it a theory, right? A tectonic theory. So what was some of that evidence that people needed? In the late 1950s, so just a little bit after Marie Tharp mapped the mid-ocean ridge, scientists also found magnetic anomalies on the seafloor that were mirrored on either side of the mid-ocean ridge. And when I say anomalies, what I mean is that on the ship floating on the surface, scientists would have a compass, right, or a instrument that would record the magnetism. And we know that today our compass points north, right? So they noticed that as they traversed over a mid-ocean ridge, there were some places where that compass would point north and have a very strong inclination towards north, right? It was like, that's north and I know it. But sometimes they would go over a part of the mid-ocean ridge where the compass would still point north, right? Because our magnetic field still drives compasses north. But it wouldn't quite be as strong, right? It'd be like there was almost a slight pull in the other direction. And what they found was that because these stripes were mirrored on either side of the mid-ocean ridge, they were able to conclude that these stripes were formed as the mid-ocean ridge was pushing old material away. So essentially, magma would well up into the Rift Valley. As it was still a liquid, the metallic minerals, the little metallic shards, such as iron shards, in that magma would align with the magnetic field. And then that magma would solidify into a solid, and those little magnetic shards were stuck in that position and they could never move again, right? They would be pushed away from the ridge. They would always be pointing towards the pole that they were attracted to when the magma was still a liquid. What's interesting is that every so often, right, every few 10 to hundreds of thousands of years, and we don't know why, Earth magnetic field switches, right? So if you were alive, say 100,000 years ago, and you pulled out a compass, your compass might actually point south or the north, which means that there are stripes on the ocean floor where when that magma solidified, the magnetic shards, the magnetic minerals didn't point north, they actually pointed south, right? And now today, when we go over them with our ships and we look at our compass or we look at our magnetic instruments, they're still being pulled towards the North Pole because of our current magnetic field. But because of the magnetic minerals beneath them, beneath the seafloor, it's fighting that magnetism a little bit so that our reading of what is north is a little weaker when we go over those ancient layers in the seafloor where the minerals are actually pointing south. Right? This explanation that I first described, it was first proposed in 1963 by Fred Vine. He was a graduate student at the time. And I want to bring this up because I want y'all to know that in order to make huge revelations in science, you don't have to be some, well-seasoned PhD, like it's not something that is so far beyond your possibility, right? Graduate students are often the ones that make these huge discoveries, such as Fred Vine, such as the paper that we read in historical geology about the Indo-Permian mass extinction, right? Like graduate students are often the ones doing the work. So if you choose to go to graduate school, know that the work you do there could be world changing, right? It's like you could be the one to make these discoveries in just a few years, and you're not that far away. All right, extrapolative thought. I'm curious. Think about everything I've said and try to apply it. We find that magnetic anomaly stripes on the East Pacific Rise, that's the mid-ocean ridge and the Pacific Ocean, tend to be thicker than those on the mid-Atlantic ridge or the mid-ocean ridge and the Atlantic Ocean. Using this information, knowing that the stripes are thicker in the Pacific and thinner in the Atlantic, which mid-ocean ridge is spreading faster?